Now that we've had a chance to look at sets, let's look at relations. So what is a relation? A relation is actually just a relation amongst sets. Right? So if you have a given relation over a number of different sets, then we take the Cartesian product of all of those sets to find all the possibilities for that relationship. And the relationship is just a subset of those. So let's take a particular example. If we have two sets, a set of people, Müller, Meyer, Schultz, Doe, and Rowe, and a set of courses, logic, linear algebra, operating systems, etc., then all the possible relationships are just the Cartesian product of sets M1 and M2. So Müller could take logic, linear algebra, operating systems, digital technology, and data structures, etc. The actual relationship is going to be some subset of that. So we might have the relationship takes course. So the actual courses taken by these people is going to be a subset of all the courses they might have taken. And in this particular example, we have Müller takes logic and operating systems and digital technology. Meyer takes operating systems and data structures, and so on. So which courses did Meyer take? Okay, took operating systems and data structures, and so on. So we often write relationships as prefix notations instead of set notation. So the set notation, we'd be saying there's a choice of a tuple that has the same cardinality as the number of arguments that are in the relation. So we might have a binary relation. It's just going to have two arguments. So we can have a value for x and a value for y that are taken over the set of possible relations, the cross product of all of the sets that could be arguments to that relation. And instead, we normally will write this in prefix notation, the name of the relation first, followed by its set of arguments. And this is probably conforms to what you've already are used to as a programmer. Think of it, maybe you shouldn't think of it as a method call, but it has syntactically that format. So a good exercise would be to try to think of some relations. Think of some relations from mathematics or from real life that hold true. And what are the sets that are involved in that relationship? And what are the elements? How are those elements related? We might think of greater than as a relationship in mathematics. And we could give it arguments that are the set of all integers for both the first argument and the second argument. So greater than 4 is greater than 3, 7 is greater than 2, and so on. How about a relationship from real life? A relationship from real life might be mother. So, Mary is John's mother, Sue is Bill's mother, and so on. Okay. See if you can think of a few more. Let's introduce a little terminology. So we need to talk about homogeneous relations. Homogeneous relations are just relations where all the arguments are drawn from the same set. And another term that's useful is binary. There are relationships that are more than binary. So between is a relationship amongst three things. But a lot of relations in nature are binary, and this has even led some people to just work with logical languages that do just strictly have binary relations. Personally, I think that's a little dangerous because the real world is more complex than that, but it's a reasonable simplification for some sort of work. And we can combine these two features of being homogeneous and binary to being a homogeneous binary relation. We'll see some interesting classes of relationships that will be homogeneous binary relations. So again, a homogeneous relation is just a relation where the arguments are all taken from the same set. So greater than, for example, is a homogeneous binary relation when you just give it the integers. The one set of integers, one individual taken from the set of integers is greater than or not than another individual taken from the set of integers. If a relation is homogeneous, we call it over a relation over a given set. Then we don't have to talk about the sets that are of each of the arguments. We don't have to talk about them separately. We can just say it's a relation over this set. All the arguments will be drawn from this set. If we have binary relations, then sometimes, especially for mathematical things, we're used to writing infix notation. We've talked a little earlier about infix and prefix notation. If we have a relationship that's like between, then we might use prefix notation. But if we're talking about the standard mathematical relationships like greater than, less than, equal to, we're just used to using infix notation. You'll see this in most programming languages. If you're in Java or Python, your mathematical operators will be special in some sense. They're usually presented in infix notation. You say 1 is greater than 2. But if you write a function in the language, then you'll use prefix notation. So, employee roster takes an employee, a company, and a time period maybe, and returns whether that employee returns a Boolean, whether that employee is a member of that company during that time period. So try to get used to thinking in both of these terms, infix notation and prefix notation, and that will make you a better computer scientist because you won't be put off by syntax in different languages that might do things slightly differently. Okay, so in the next few slides, we're going to just look at homogeneous binary relations because there are a lot of them. It's an interesting class of relationship. So here's an example of a bunch of them I've already alluded to. So a relationship over the natural numbers is equal. So it's 0 and the positive integers. So it's just wherever each of the arguments are the same. So 0, 0, 1, 1, 2, 2. We could look at the positive and negative integers, for example, and look at the less than relation. We might define this with the first sub-bullet formula here. That means that for I and I plus j, where I is in the set of positive and negative integers, and j is in the set of positive integers, it holds true that the less than relationship holds between I and I plus j. We could also give some specific examples. So 1, 2 is within the set less than, the set of values that hold over the natural numbers as arguments for the less than relation. That would be one way to talk about it, where we're giving specific examples within this set of tuples that are true for the given relationship. And then in the third bullet here, we could just sort of list many of them. So -1 is less than 0, 0 is less than 1, 0 is less than 2, and so on. Not equals is another homogeneous binary relation. So if our set is W, where W is a name, and we're taking our previous example of German students in computer science courses, Müller is not the same as Meyer, Müller is not the same as Schultz, and so forth. And we could also look at the subset relation. So that's over the power set of M. We introduced power set a while back. And A comma B is a subset of A, B, C, and so on. Let's introduce some more technology, or terminology, I should say. Left total and right unique. So if R is a homologous binary relation over A and B, then it's true that for all A, that means that it's within the set of capital A, and there exists some B that exists in the set of capital B, such that R holds between A and B. If that's the case, then R is left total. For every argument A, there is some element B that holds in this relation. So every element of A is associated with at least one element of B. Another property, right unique. So for every A in the set A, and for all B in B, there's some C that's in B, such that relation AB holds and relation AC holds, and that means that B is equal to C. If that's the case, then R is right unique. So we can summarize this. Left total, every element from A has at least one element of B in the relation, and a right unique relation means that every element at A is related to at most one element in B. Right unique means it's functional. Some useful properties of a homologous binary relation here that we'll see are the notion of being reflexive. So every element is related to itself with this relation. Symmetric, if A is related to B, then B is related to A. Transitive, if A is related to B and B is related to C, then A is related to C. If that's the case, then R is transitive. And then it's also an interesting case if we have all three of these properties holding at once, and that's known as an equivalence relation. We call these things orders. Those are our transitive relationships are called orders, right? We're creating an ordering amongst the elements of the set. We're saying that if we have a relation A to B and B to C, then we also have this relationship A to C. Every set of relations that we have forms an ordering or a priority. Tree structures, for example, are orderings where there's an order between the things at the higher level of the tree compared to the things at the lower level of the tree. And equivalence relationships divide sets into classes of equal elements. However, there are more relations out there that are equivalence relations than just the equals relation, but that's the one that we're all most familiar with. So as an exercise, take a look at my ontology. Go into this tool called Sigma. Take a look at each of these web pages. I haven't introduced the syntax to you, but hopefully if you just look at the first few statements in this tool, you'll be able to quickly understand, what are the reflexive relations, what are the symmetric relations, what are the transitive relations in one particular way of formalizing our world. The names should give you a good hint for what the relationships are, and see if you can come up with the answer just by looking at this tool, even though it's going to be a bit unfamiliar. So here we are. Here's a view of the web page in the Sigma browser, and we have the page for reflexive relation. Try clicking on those names. One of them is called connected, so two things are connected to each other. And this is reflexive because something is always connected to itself. See if you can figure out why each of these relations that you browse to are reflexive or symmetric or transitive. Does it fit with your idea of reality? If it doesn't, put a question in the comment below and I'll do my best to answer. So here's another exercise. Check whether the following relations are left total, right unique, reflexive, symmetric, or transitive, and provide some kind of reason if in fact they are, or provide some sort of counterexample that says why they're not. If you'd like something that's a little bit more challenging, try to show or refute that every equivalence relation is left total, or that every equivalence relation is right unique. And again, if you have some questions, put them in the comments below, and I'll try to give you some feedback.